Before I begin, I need to declare that everything I present here is original and entirely my own work, and that I have neither used any sources nor copied any code without proper acknowledgement. Let's start with the project background. Breast cancer. It is the most common type of cancer in women worldwide and the second most commonly occurring cancer overall. In developing countries, it is the deadliest cancer among females, and similarly, even in the developed countries such as Australia and the United States, breast cancer is the second most fatal type of cancer for women. Detecting cancerous breast tumors at an early stage not only plays the most integral role in accurate prognosis and treatment for breast cancer, but it also is the key to reducing breast cancer mortality rates and increasing the survival chances of breast cancer patients. Although mammograms, ultrasound, and medical resonance imaging may or may not suggest the presence of breast cancer, a definite diagnosis can only be made by a qualified medical examiner after thoroughly inspecting the results of a breast biopsy. Fine needle aspiration, in short FNA biopsy, has been known to be not only quicker and safer, but also less painful and more cost-effective than other alternative breast biopsies. With an aim to amplify the advantages of FNA biopsy and improve the utility and relevance of FNA as a diagnostic tool for breast cancer, Dr. Wahlberg and his colleagues computed the features of cell nuclei from digitized images of breast mass fine needle aspirates, and they later made their dataset, mostly referred to as the Wisconsin Breast Cancer Dataset, WBCD, available to public. Since then, machine learning researchers have been working on this dataset to develop a model that can classify benign and malignant tumors with a higher rate of prediction accuracy. The main purpose of this project is to build and then test the performance of a novel multi-level classification system, which is based on the features of the WBCD to predict breast cancer diagnosis. With this classification system, we aim to help medical practitioners who use FNA biopsy for breast cancer diagnosis through their decision-making. Earlier studies on the Wisconsin Breast Cancer Dataset used various algorithms such as support vector machine, neural network, random forest, and others. They attained relatively high prediction accuracies with their best performing model. However, it should be noted that due to lack of adequate cross-validation of the performance of machine learning classifiers, overfitting models with inflated prediction accuracies were frequently reported in literature. For example, Liu and others stated that their random forest model through principal component analysis yielded 99% prediction accuracy. However, their model was based on a single data partition. Similarly, although Prakash and Visakha, Abdar and Makarenko also attained high prediction accuracies like 98%, even 100%, their results were predicated on one data partition lacking adequate cross-validation. Such inadequacy also existed for models when they were folded only 3 times, or when only the maximum performance, but not the mean of the model's performance was reported. Developing a model that is not adequately cross-validated through random multiple data partitions will likely create overfitting issues. Although an insufficiently cross-validated model may provide high accuracy on the training data, it may yield subpar results for new data. Nevertheless, instances of effective utilization of cross-validation techniques exist in literature. For example, Chalabi and others used a support vector machine model to attain a 96.6% accuracy through a 10 times 10-fold stratified Monte Carlo cross-validation. Looking at the Wisconsin Breast Cancer Dataset, we notice that our primary variable of interest, which is the response, or in other words, a dependent variable, is the diagnosis variable. It contains information pertaining to whether an observed tumor is benign or malignant. We know that there are no missing values in the dataset, and we notice that 37% of the diagnosis data belongs to malignant tumors and 63% to benign tumors. As the explanatory or independent variables, we have 10 real-valued features that have been computed for each nucleus. These are radius, texture, perimeter, area, and so on. In addition, the mean, standard error SE, and worst of these features have also been calculated and recorded for each image, resulting in 30 features in total. For example, the radius feature extends to radius mean, radius SE, and radius worst. In our analysis, we split the data randomly every time we build and test a model, as we assigned 70% of the data to the training and 30% to the test sets. The classification system is made of 3 classifiers. Each classifier is being trained to independently predict whether a breast tumor is benign or malignant. The performance of each classifier is being determined upon the prediction accuracy of its trained models on its corresponding test data. Therefore, the outcome, whether it be benign or malignant, for each classifier comes with a certain prediction accuracy in percentage terms. Support vector machine, SVM, is a supervised machine learning model with a discriminative classification algorithm. We choose to deploy SVM for the first 2 classifiers because we want to achieve 100% prediction accuracy for either benign or malignant tumors by separating them from one another as much as we can. The third and final classifier is an ensemble learning classifier, which provides an outcome based on the simple majority voting of the 7 best performing feature-based or principal component-based models built via machine learning algorithms such as naive Bayes, k-nearest neighbors, random forest, support vector machine, regression trees, and neural network. By applying 10 times 10-fold stratified Monte Carlo cross-validation, we intend to attain more representative performance estimations to provide us with a better understanding of how well our classifiers can be generalized to other datasets containing similar features. Let's talk about the results now. When a new case enters the system, it will first go through the OSVM classifier, which stands for Overdiagnosing Support Vector Machine Classifier. What's special about this classifier is that it deliberately overdiagnoses and produces 0 false negatives, so that if a tumor gets classified as benign, the possibility of the tumor being actually malignant will be ruled out. When the data is randomly partitioned, trained, tested, and cross-validated, the OSVM classifier produces no false negatives, meaning no chance for a tumor to be actually malignant if classified as benign. At the same time, it identifies some of the actual benign tumors within true negatives. For example, the number of true negatives in this confusion matrix is 52. Therefore, these 52 cases can be declared to be benign with full confidence, and these patients, at the discretion of a physician, of course, may not have to receive any further treatment, and they can be discharged from the hospital immediately. However, if the tumor is classified as malignant by the OSVM classifier, the case will have to be run through by the USVM classifier, which stands for Underdiagnosing Support Vector Machine Classifier. The USVM does the opposite as it intentionally underdiagnoses to produce 0 false positives. When the Wisconsin data is randomly partitioned, trained, tested, and cross-validated, the USVM classifier yields no false positives, meaning no chance for a tumor to be actually benign if classified as malignant. Simultaneously, it identifies some of the actual malignant tumors within true positives. For example, the number of true positives here in this confusion matrix is 32. Ergo, these 32 cases can be declared to be malignant with full confidence, and yet again, at the discretion of a physician, cancer treatment may commence for these patients right away. As the last level of the classification system, the ensemble learning classifier will take effect if the USVM classifier classifies some of the cases as benign. We use F2 performance because we are slightly more inclined to not miss malignant tumors, so we slightly overdiagnose with the ensemble learning classifier. After all, if we misdiagnose actual benign tumors, there's a comeback. But if we misdiagnose actual malignant tumors, there may be no comeback, as those patients may never receive any treatment at all, and that may cost them their life. As a result of the majority voting of the top 7 performing models in terms of F2 score, we attained a remarkable 98.8% accuracy for not missing malignant tumors. We also record that the ensemble learning classifier yields a 97.4% overall accuracy. What makes this classification system so unique and useful is that it is made of an overdiagnosing classifier, which puts more weight to detecting malignant breast tumors and thus rules out the possibility of predicting an actual malignant tumor as benign with 100% accuracy, an underdiagnosing classifier, which puts more weight to detecting benign breast tumors and thus rules out the possibility of predicting an actual benign tumor as malignant with 100% accuracy, and finally, an ensemble learning classifier, which is made of the top performing individual predictive algorithms for breast cancer diagnosis and is at the same time cross-validated with a robust technique. The first and foremost limitation of this research project is that the performance estimations were all based on a single dataset, the Wisconsin Breast Cancer Dataset. Therefore, the performance of the proposed classification system should also be tested on other patient datasets containing similar FNA biopsy features. Another limitation is that the separation points 0.05 and 0.9 within the prediction range of the OSVM and USVM classifiers respectively were determined by trial and error. Consequently, that process was long, time-consuming, and could be optimized to achieve a higher number of true positives and true negatives. Hence, an optimization function is recommended to be built and used in future research to deal with this particular challenge. Finally, other algorithms with high individual prediction performance could be included in the ensemble learning classifier to boost its overall performance. To conclude, this project may encourage hospitals to rely more on the artificial intelligence to be utilized through the diagnosis process of breast cancer via FNA biopsy. In accordance with the Wisconsin data, the diagnosis verdict can be finalized quicker for the suspected tumors that are classified as benign by the OSVM classifier and malignant by the USVM classifier. Furthermore, the outcome provided by the ensemble learning classifier, if needed, can also help physicians not only make better informed decisions about the status of a suspected breast tumor, but it will also help them take necessary action quicker with more confidence. Finally, the novel idea and strategy of keeping false negatives and false positives at 0% with modified classification algorithms and then using a third classifier to predict the cases that pass through the first two classifiers may make a real contribution to the broader field of predictive analytics. And that concludes this presentation. Thank you all for your participation.